So hello everyone and welcome to NEETOPEDIA, that is NEET Encyclopedia, and I hope you are enjoying the audiobooks mentioned on this channel. And today we'll start with Polymers of Class 12th Chemistry. So let's get started. Unit 15, Polymers. Copolymerization has been used by nature in polypeptides which may contain as many as 20 different amino acids. Chemists are still far behind. Do you think that daily life would have been easier and colorful without the discovery and varied applications of polymers? The use of polymers in manufacture of plastic buckets, cups and saucers, children's toys, packaging bags, synthetic cloth materials, automobile tires, gears and seals, electric insulating materials and machine parts has completely revolutionized the daily life as well as the industrial scenario. Indeed, the polymers are the backbone of four major industries, that is, plastic, elastomers, fibers, and paints and varnishes. The word polymer is coined from two Greek words. Poly means many and mer means unit or a part. The term polymer is defined as very large molecules having high molecular mass. These are also referred to as macromolecules, which are formed by joining repeating structural units on a large scale. The repeating structural units are derived from some simple and reactive molecules known as monomers and are linked to each other by covalent bonds. The process of formation of polymers from respective monomers is called polymerization. 15.1 Classification of polymers. There are several ways of classification of polymers based on some special considerations. One of the common classifications of polymers is based on source from which the polymer is derived. Under this type of classification, there are three subcategories. Number 1. Natural polymer. These polymers are found in plants and animals. Examples are proteins, cellulose, starch, some resins and rubber. Number 2. Semi-synthetic polymers. Cellulose derivatives as cellulose acetate and cellulose nitrate etc. are some useful examples of this subcategory. Number 3. Synthetic polymers. A variety of synthetic polymers such as plastic, synthetic fibers and synthetic rubbers are examples of man-made polymers extensively used in daily life as well as in industry. Polymers can also be classified on the basis of the structure, molecular forces or modes of polymerization. 15.2 Types of polymerization reactions. There are two broad types of polymerization reactions, that is, the addition or chain growth polymerization and condensation or step growth polymerization. In this type of polymerization, the molecules of the same monomer or different monomer add together on a large scale to form a polymer. The monomers are used are unsaturated compounds, examples alkenes, alkynes, and the derivatives. This mode of polymerization leads to an increase in chain length, and chain growth can take place through the formation of either free radicals or ionic species. However, free radical governed addition or chain growth polymerization is the most common mode. Number 1. Free radical mechanism. A variety of alkenes or dienes and their derivatives are polymerized in presence of free radical generating initiator like benzoyl peroxide, acetyl peroxide, tert-butyl peroxide, etc. For example, the polymerization of ethene to polyethylene consists of heating or exposing to light in a mixture of ethene with a small amount of benzoyl peroxide as initiator. The process starts with addition of phenyl free radical formed by peroxide to the ethene double bond, thus generating a new and larger free radical. This step is called chain initiating step. As this radical reacts with another molecule of ethene, another bigger sized radical is formed. The repetition of this sequence with new and bigger radicals carries the reaction forward, and the step is termed as step chain propagating step. Ultimately, at some stage, the product radical thus formed reacts with another radical to form the polymerized product. This step is called chain terminating step. The sequence of steps involved in the formation of polyethylene are depicted as follows. Chain initiation steps, where a benzoyl peroxide is broken down into phenyl radical and further phenyl radical reacts with ethene to form another free radical. While in chain propagating steps, the free radical formed combines with another molecule of ethene and propagates the step further. Chain terminating step. For termination of the long chain, these free radicals can combine in different ways to form polyethylene. One mode of termination of chain is shown. The addition polymers formed by polymerization of a single monomeric species is known as homopolymers. For example, polythene discussed above is a homopolymer. The polymers made by addition polymerization from two different monomers are known as copolymers. Buna-S, which is formed by polymerization of buta-1,3-diene and styrene, is an example of copolymer formed by addition polymerization. 15.2.1.2 Some important addition polymers. Number A. Polythene. Polythene are linear or slightly blanched long chain molecules. These are capable of repeatedly softening on heating and hardening on cooling, and thus thermoplastic polymers. There are two types of polythene as given below. Number 1. Low density polythene. This is obtained by the polymerization of ethene under high pressure of 1000 to 2000 atmospheres at a temperature of 350 Kelvin to 570 Kelvin in the presence of traces of dioxygen or a peroxide initiator as catalyst. The low density polythene is obtained through free radical addition and H atom abstraction. It has highly branched structure. These polymers have straight chain structure with some branches as shown below. Low density polythene is chemically inert and but not flexible and a poor conductor of electricity. Hence, it is used in insulation of electricity carrying wires and manufacture of squeeze bottle, toys and flexible pipes. Number 2. High density polythene. It is formed when addition polymerization of ethene takes place in a hydrocarbon solvent in presence of catalysts such as triethyl aluminium and titanium tetrachloride, that is Ziegler-Natta catalyst, at a temperature of 333 Kelvin to 343 Kelvin under a pressure of 6 to 7 atmospheres. High density polythene thus produced consists of linear molecules as shown below and has high density due to close packing. Each polymers are also called linear polymers. High density polymers are also chemically inert and more tough and hard. It is used for manufacturing buckets, dustbins, bottles, pipes, etc. B. Polytetrafluoroethene, that is Teflon. Teflon is manufactured by heating tetrafluoroethene with a free radical of persulfate catalyst at high temperatures or pressures. It is chemically inert and resistant to attack by corrosive agents. It is used in making oil seals and gaskets and also used for non-stick surface coated utensils. Number C. Polyacrylonitrile. The addition of polymerization of acrylonitrile in presence of a peroxide catalyst leads to the formation of polyacrylonitrile. Polyacrylonitrile is used as a substitute for wool in making commercial fibers or lawn as acrylan. Skipping example 5.1 for you to solve it later, or you can pause the video and solve it right now. 15.2.2 Condensation Polymerization or Step Growth Polymerization. This type of polymerization generally involves a repetitive condensation reaction between two bifunctional or trifunctional monomeric units. Such polycondensation reactions may result in the loss of some simple molecules such as water, alcohol, hydrogen, chloride, etc., and lead to the formation of higher molecular mass condensation polymers. In these reactions, the product of each step is again a bifunctional species and a sequence of condensation goes on. Since each step produces a distinct functionalized species, it is independent of each other. This process is also called as step growth polymerization. The formation of pterylene or dacron by interaction of ethylene glycol and terephthalic acid is an example of this type of polymerization. 15.2.2.1 Some important condensation polymers. Number A. Polyamides. These polymers possessing amide linkages are important examples of synthetic fibers and are termed as nylons. The general method of preparation consists of the condensation polymerization of diamines with dicarboxylic acid or condensation of amino acids or their lactams. Nylons. Number 1. Nylon 6,6. It is prepared by condensation polymerization of hexamethylene diamine with adipic acid under high pressure and at high temperature. Nylon 6,6 is a fiber forming solid. It possess high tensile strength. This characteristic can be attributed to the strong intermolecular forces like hydrogen bonding. These strong forces also lead to close packing of chains and thus impart crystalline structure. Nylon 66 is used in making sheets, bristles for brushes and in textile industry. Number 2. Nylon 6. It is obtained by heating caprolactam with water at a high temperature. Nylon 6 is used for manufacture of tire cords, fabrics and ropes. B. Polyesters. These are polycondensation products of dicarboxylic acids and oils. Dacron or terylene is best known example of polyesters. It is manufactured by heating a mixture of ethylene glycol and terephthalic acid at 420 Kelvin to 460 Kelvin in presence of zinc acetate antimony trioxide catalyst as per the reaction given earlier. Dacron fiber, that is terylene, is crease resistant and is used in blending with cotton and wool fibers and also as glass reinforcing materials in safety helmets, etc. C. Phenol formaldehyde polymer, bakelite and related polymers. Phenol formaldehyde polymers are the oldest synthetic polymers. These are obtained by condensation reaction of phenol with formaldehyde in the presence of either an acid or a base catalyst. The reaction starts with initial formation of ortho and or para hydroxymethylphenol derivatives which further reacts with phenol to form compounds giving rings joined to each other through CH2 groups. The initial product could be a linear product, that is Novolac, which is used in paints. Now here, to remember this, you can use that Nerolac paint ad to remember Novolac, which is used in paints. Okay, moving on further. Novolac on heating with formaldehyde undergoes cross-linking to form an infusible solid mass called bakelite. It is a thermosetting polymer which not only reduced or remolded. Thus, bakelite is formed by cross-linking of linear chains of polymer Novolac. Bakelite is used for making combs, phonograph records, electrical switches and handles of various utensils. D. Melamine formaldehyde polymer. Melamine formaldehyde polymer is formed by condensation polymerization of melamine and formaldehyde. It is used in manufacture of unbreakable crockery. I am skipping 15.2 and 15.3 for you to solve it later, or you can pause the video and solve it right now. 15.2.3 Copolymerization. Copolymerization is a polymerization reaction in which mixture of more than one monomeric species is allowed to polymerize and form a polymer. The copolymer can be made not only by chain growth polymerization but by step growth polymerization also. It contains multiple units of each monomer used in same polymeric chain. For example, a mixture of buta-1,3-diene and styrene can form a copolymer. Copolymer have properties quite different from homopolymers. For example, butadiene styrene copolymer is quite tough and is a good substitute for natural rubber. It is used for the manufacture of auto tires, floor tiles, footwear components, cable insulation, etc. 15.2.4 Rubber. Number 1. Natural rubber. Rubber is a natural polymer and possesses elastic properties. It is also termed as elastomeric polymer. In elastomeric polymers, the polymer chains are held together by weak intermolecular forces. These weak binding forces permit the polymer to be stretched. A few crosslinks are introduced in between the chains which help the polymer to retract to its original position after the force is released. Rubber has a variety of uses. It is manufactured from rubber latex, which is a colloidal dispersion of rubber in water. This latex is obtained from the rubber tree, which is found in India, Sri Lanka, Indonesia, Malaysia and South America. Natural rubber may be considered as a linear polymer of isoprene, that is 2-methyl-1,3-butadiene, and is also called as cis-1,4-polyisoprene. Cis-polyisoprene molecules consist of various chains held together by weak van der Waals interactions and has a coiled structure. Thus, it can be stretched like a spring and exhibits elastic properties. Vulcanization of rubber. Natural rubber becomes soft at high temperatures, that is above 335 Kelvin, and brittle at low temperatures, and shows high water absorption capacity. It is soluble in nonpolar solvents and is non-resistant to attack by oxidizing agents. To improve upon these physical properties, a process of vulcanization is carried out. This process consists of heating a mixture of raw rubber with sulfur and an appropriate additive. At a temperature range between 373 Kelvin to 415 Kelvin, on vulcanization, sulfur forms cross-links at reactive sites of double bonds, and thus the rubber gets stiffened. In manufacture of tire rubber, 5% of sulfur is used as cross-linking agent. The probable structures of vulcanized rubber molecules are depicted below. Number 2. Synthetic rubbers. Synthetic rubber is a vulcanizable rubber like polymer which is capable of getting stretched to twice its length. However, it returns to its original shape and size as soon as the external stretching force is released. Thus, synthetic rubbers are either homopolymers of 1,3-butadiene derivatives or copolymers of 1,3-butadiene or its derivatives with another unsaturated monomer. Preparation of synthetic rubbers. Number 1. Neoprene. Neoprene or polychloropren is formed by free radical polymerization of chloropren. It has superior resistance to vegetable and mineral oils. It is used for manufacturing conveyor belts, gaskets and hoses. Number 2. Buna N. You have already studied about Buna S in section 15.1.3. Buna N is obtained by copolymerization of 1,3-buta, 1,3-diene and acrylonitrile in presence of a peroxide catalyst. It is resistant to the action of petrol, lubricating oil and organic solvents. It is used in making oil seals, tank lining, etc. Now I am skipping questions 15.4 and 15.5 for you to solve it later, or you can pause the video and solve it right now. 15.3 Molecular mass of polymers. Polymer properties are closely related to the molecular mass, size and structure. The growth of polymer chain during the synthesis is dependent upon the availability of monomers in the reaction mixture. Thus, the polymer sample contains chains of varying lengths and hence its molecular mass is always expressed as an average. The molecular mass of polymers can be determined by chemical and physical methods. 15.4 Biodegradable polymers. A large number of polymers are quite resistant to the environmental degradation processes and are thus responsible for accumulation of polymeric solid waste materials. These solid waste causes acute environmental problems and remain undegraded for long time. In view of general awareness and concern for the problems created by polymeric solid waste, certain new biodegradable synthetic polymers have been designed and developed. These polymers contain functional groups similar to the functional groups present in biopolymers. Aliphatic polyesters are one important class of biodegradable polymers. Some important examples are given below. Number 1. Polybeta hydroxybutyrate co-beta hydroxyvalerate or THBV. It is obtained by copolymerization of 3-hydroxybutanoic acid and 3-hydroxypentanoic acid. THBV is used for specialty packing, orthopedic devices and in controlled release of drugs. THBV undergoes bacterial degradation in environment. Number 2. Nylon 2 Nylon 6. It is an alternating polyamide copolymer of glycine and aminocaproic acid and is biodegradable. Can you write the structure of its polymer? 15.5 Polymers of commercial importance. Besides the polymers already discussed, some other commercially important polymers are given along with the structures and uses given below in table 15.1. Now I am skipping this table for you to memorize it in a better way, and if you want tricks to remember the monomers of the given polymers, do let me know in the comment section and you will be provided with it pretty soon. Summary. Polymers are defined as high molecular mass macromolecules which consist of repeating structural units derived from corresponding monomers. These polymers may be of natural or synthetic origin and are classified in a number of ways. In the presence of an organic peroxide initiator, the alkenes and their derivatives undergo addition polymerization or chain growth polymerization through a free radical mechanism. Polythene, Teflon, Orlon, etc. are formed by addition polymerization of an appropriate alkene or its derivative. Condensation polymerization reactions are shown by interaction of bi or polyfunctional monomers containing NH2OH and COOH groups. This type of polymerization proceeds through elimination of certain simple molecules such as the condensation polymerization progress through step by step and is also called as step growth polymerization. Nylon, bakelite and dacron are some important examples of condensation polymers. However, a mixture of two unsaturated monomers exhibits copolymerization and forms a copolymer containing multiple units of each monomer. Natural rubber is a cis 1,4 polyisoprene and can be made more tough by process of vulcanization with sulfur. Synthetic rubbers are usually obtained by copolymers of alkene and 1,3-butadiene derivatives. In view of potential environment hazards of synthetic polymeric waste, certain biodegradable polymers such as THBV and nylon 2 nylon 6 are developed as alternatives. So that's it for this chapter. I hope you enjoyed listening to this audiobook. Do let us know your suggestions in the comment box. Till then, subscribe to the channel and stay tuned. Thank you.